Swayam Prabha. Digital India. Educated India.
Friends, welcome to the 19th lecture on the course Advanced Steel Design. Here we are going to continue with the plastic design. I will call this plastic design 3, okay, third lecture. In the last lecture we learned the comparison between the plastic design philosophy with elastic design and ultimate load design. We have learned that in plastic design the material strength, which is in terms of ductility or plastic deformation, is utilized, which is one of the basic requirements in a form dominant structural system. Apart from utilizing the reserve capacity of the geometry in terms of structural indeterminacy, the material reserve strength in terms of ductility is also being used in plastic design effectively. So, we said that in plastic design we have got a new concept called equal area axis, where the total compressive force in a cross section meets exactly in magnitude with the total tensile force acting in the cross section. So, each and every layer in the cross section is having freedom to reach the yield stress, because we have assumed that each and every fiber is independent to elongate or contract, so that the stress value can be reached till sigma y. Once the stretch sigma y is reached, then the next section or the fiber is increased with the stress of sigma y and so on. So, the whole cross section gets plastified. So, let us now derive the plastic moment capacity of any cross section. To start with, we will assume a rectangular cross section, then we will go to arbitrary sections. Okay? So, to start with, we will do with the rectangular cross section. So, let me draw a rectangular cross section, a solid cross section of dimensions B and D. So, let us draw the stress diagram at elastic state and plastic state. So, this means elastic state, because only the extreme fiber is yielded. Okay. As usual, this is my compressive force and tensile force. Okay, this is sigma y. In the fully plastic state, we already know that the total tensile force will be equal to total compressive force, and every fiber will be sigma y. Okay. So, we call this centroid as y1 and this centroid as y2. So, now this axis is termed as equal area axis, because about this axis you see the total compressive force is equal to the total tensile force. Okay. Let the material strength is taken as sigma y. So, we can easily find the section modulus. I will just rub this and write it here because I need some space. Let me write it here, okay. I put it as equal area axis. So, we can quickly find ZE, which is the elastic section modulus, which can be given by the moment of inertia about the z axis by the distance of extreme fiber. So, for this cross section we can easily find out it is going to be BDQ by 12 divided by D by 2, which becomes BD square by 6. Let us call this equation number 1. If you want to find the elastic moment capacity, this is given by a simple expression, this section modulus multiplied by the corresponding stress. We know that. Let us look at the plastic stress distribution. Okay. Let us look at this let us look at the Keon figure, this figure 3. So, now with reference to figure 3, let us find out the moment, which will be equal to C into y bar 1, let us say bar 1, plus T into y bar 2. Since C is equal to T, we can say this is twice of C into y bar 1. Can I say that? So, what is the compressive force, which is going to be 2 times of. So, you know here the breadth of section is B, is it not? See here. So, B and D by 2, because this is D by 2, am I right? So, I am looking at this area now. B into D by 2 into the centroid y bar will be D by 4, I think that is okay, simple geometry, and I multiply this with stress, because this has got to be force into stress, okay. So, which gives me B D square by 4 into sigma y, okay. So, if I say this equation number 3, so I replace this m as mp and I will term this as zp to sigma y. This is only to keep the similarity of this equation with that of this, okay. Instead of keeping some bd etc., I want to keep it like this, okay. So, zp is called plastic section modulus, mp is called plastic moment of resistance, and of course, sigma y is the yield stress. Okay, you can easily see there is a perfect compatibility between the equations 2 and 3. A, both of them indicate the same manner, and one refers to elastic section modulus, other refers to plastic section modulus. Therefore, the corresponding moments are elastic moment of resistance and plastic moment of resistance, is it not? So, it is okay. But we do not want to say, please understand, we do not want to say, do not state that Zp is Pd square by 4. We will not do this, okay. We will not do this. We will not remember Zp in this manner. We will simply say plastic moment of resistance is plastic section modulus multiplied by sigma y. We will come to this argument slightly later. How do you get this? Okay. Now friends, we can easily find out the moment capacity Let us take these two equations 2 and 3a. Let us consider equations 2 and 3. Okay. So, equations 2 say it is mz is ze sigma y and this says mp is zp sigma y. The ratio of Zp to Zd. The ratio of Zp to Zd is called shape factor. On the other hand, I would say Zp is shape factor multiplied by Zd. That is why I said let us not remember Zp as Bd square by 4 a rectangular section. So, our job is to now find out the shape factor for various cross sections. So, for a given cross section which is T, L, circle or any arbitrary, if I am able to find out the shape factor, I already have the second moment of area divided by the y max, I get Ze, I can easily find the moment capacity. Okay. And also please note friends, the moment capacity of plastic section is plastic section modulus multiplied by Zy, it is not a function of applied load, am I right? Usually m used to be WL square by 12 etc. whatever may be. It is not a function of load, it is purely a geometric property. Of course, sigma y is present. So, that is why we always wanted to introduce a factor called shape factor. So, shape is related to something of geometry. Okay, that is the reason why we want to introduce a term called shape factor. So, for different cross sections, if I am able to find the shape factor, derive them, or is it available in steel tables or any standard handbooks, I can easily find the moment capacity, because we all know in structural steel handbooks the moment of inertia or second moment of area of the cross section and depth of the section. Therefore, Ze section modulus is available in the steel tables, is it not? Please look at structural engineering handbook IS SP 61. If you look at for different cross sections of I, C, L angles, you will find Ze, that is elastic section modulus is available readily. If by any chance, if the table also gives you a shape factor of that section, you also have Zp with you, and if you have Zp, you can have Mp with you. So, it is just a minute to calculate the moment capacity of the section for plastic design. Okay. So, let us try to understand a very important concept here, that the additional moment capacity from M elastic to M plastic is obtained purely as a geometric capability, provided the material is ductile. So, the additional gain comes from the structural redundancy, which is degree of static. Indeterminacy is one part of it, form dominance is other part of it. Now friends, let us also make a comment that the maximum stressed section is identified as the critical section. So, what do you mean by a critical section? This critical section cannot carry any additional moment or let us say load beyond MP. Okay. This is because at this critical section the full cross section has already yielded. So, such sections are termed as plastic hinges. And the corresponding section is fully plasticized. Okay. But please note, at plastic hinges, the stress level is only sigma y. But still the term plastic is being used because the deformation at the section is in a plastic stage. Okay. Having said this, let us try to derive the shape factor. Let us quickly see what is a shape factor. Shape factor is a factor that enables higher moment carrying capacity which is strongly geometry dependent. That is why it is called shape factor. Okay. Let us derive a shape factor for an arbitrary section. Okay. Let us derive a shape factor of an arbitrary section, then we will apply this logic to all sections. We will take an arbitrary section, let us say extreme fiber, we have a plastic stress distribution, and we also mark the equal area axis. Okay, this is C compressive force and this is tensile force. Okay. Let us say the corresponding area here is A1 and the corresponding area here is A2. Okay. So, now at equal area axis, the section is divided into equal halves, is it not? So, that is the total compressive force is equal to the total tensile force T. So, I can now say the total area A is A1 plus A2. Okay. Can I say this as A by 2? That is, we can also say A1 is equal to A2, which is A by 2. Now, let us take moment about of C and T about equal area axis. See what happens. We should say C into y bar 1 plus T into y bar 2 should be the total moment. We also know C is sigma y into A by A1 and T is sigma y into A2. Let us substitute them. Let us substitute equation 3 in equation 2. Okay. So, sigma y A1 y bar 1 plus sigma y A2 y bar 2 is m. Let me carry it in the next page. Sigma y A1 y bar 1 plus sigma y A2 y bar 2 is m. So, let us say sigma y A by 2 y bar 1 plus y bar 2 is m. So, can I say this as sigma y into Zp? If I use this term as Zp, then this becomes my Mp, am I right? Okay. Now, interestingly friends, the shape factor is Zp by Zt. Zp by Zd is the shape factor. Okay. So, now we can try to find out the shape factor for different cross sections. Before we do that, let us try to find out what is an elastic core. So, let us try to understand what is an elastic core and what its depth. So, for a plastic design to be effective, the depth of elastic core at the critical section should be 0, is it not? Because at that section it is fully plasticized. So, elastic core should be 0. Then only at these sections plastic hinges can form. Now, the number of plastic hinges that can form depends on the static degree of indeterminacy. Let us call this as n. So, the number of plastic hinges in a given structure should be equal to number of degree of static indeterminacy plus 1. When so many hinges have been formed, the structure will get converted into a mechanism. So, more the degree of static indeterminacy, more the possibility of plastic hinges, because we need n plus 1 hinges. Okay? So, it becomes a mechanism. It will also enhance the moment carrying capacity of the structure. Apart from enhancing, it has attained the shape factor. In simple terms, the moment carrying capacity is achieved by the plastic design in two ways. One, by having a higher shape factor, which is geometry dependent. Two, the structure should have higher degree of static indeterminacy. Friends, you will recollect that both of these are related to the structural form, is it not? Therefore, one can say plastic design is a form dominant concept. It utilizes strength till sigma y of the material and it invokes the reserve energy from the material in terms of ductility, from the structure in terms of static degree of indeterminacy and form compliancy. Okay, that is very interesting. So, let us try to derive the elastic core and check what is that condition for a plastic design. Okay. So, to derive an elastic core, let us take again a rectangular cross section. The cross section has the dimensions b and depth as d. Let us H. Let us design a hybrid section where the section is partially plastic and the remaining is elastic. Let us have an elastoplastic section. Okay. So, let us have an elastoplastic section. Okay. We call this elastic part as E, where E is called depth of elastic core. Of course, we know that the stress at the extreme fiber remains sigma y. Okay. And we also know from this figure that this dimension is h by 2 and this dimension of course is E by 2. Am I right? Okay. Let us consider this cross section and the stress distribution diagram, which is elastoplastic as shown in the figure, right. First, let us find out the depth of elastic core. So, this is the elastic part and this is my plastic part. Okay. Let us find out the moment of resistance of elastic part or elastic core at any cross section. How do you get that? Let us say that is M1, which will be area of a triangle. So, half base, height is E by 2 and the CG of that is going to be 2/3 E by 2. Am I right? It is a triangle, no? I am taking moment about this point. 2/3 E by 2 and I have two such things, one on the top and one on the bottom, and there is only the force. So, I will multiply this with the stress to get my moment, right. Okay. So, half base E by 2, 2/3 E by 2 and twice of that. So, let us cut the common values. So, can I get this as B E square by 6 sigma y, B E square by 6 sigma y, or equation number 1. Now, let us work out the moment of resistance of the plastic section or plastic core. I call this as M2, which is the red one, right. So, let us find out that. So, let us say it is a rectangle. So, B into h by 2 minus E by 2, right. And the CG of this from here will be equal to E by 2 plus h by 2 minus E by 2 of half. Am I right? Okay, E by 2 plus h by 2 minus E by 2, half of that, correct. So, that is going to be the distance, and I will multiply this with the stress, and there are two such pieces, one on the top and one on the bottom. Okay. Let us simplify this. So, 2h by 2 minus E by 2, E by 2 plus h by 2 minus E by 2, half of that, correct. Fine. So, let us simplify this. Please simplify and see what happens. So, it becomes 2 sigma y B into h minus E by 2 of E by 4 plus h by 4, which will further become twice sigma y B h minus E by 2 h plus E by 4, am I right, which can be further 2 sigma y B, okay, or let us remove this 2 because this goes away. A plus B into A minus B, we can say A square minus B square, okay, by 4. So, that becomes maybe equation 1, equation 2, equation 3, equation 4, equation 5. So, that becomes my M2. So, now friends, the total moment carrying capacity of this elastoplastic section will be sum of these. So, the moment capacity of the elastoplastic section will be M, which is M1 plus M2. So, let us sum these two. What happens? Let us see. So, M is going to be sigma y is anyway common in both cases. The first one was B E square by 6. The second one was B H square minus E square by 4. Am I right? Which on simplification will become sigma y B H square by 4 minus B E square by 12. Okay, B H square by 4 minus B E square by 12. Again on simplification, sigma y B H square by 4 of 1 minus E square by 3 H square. Please check this. Let us call equation number, this was 5, so I call this as 6, this as 7, this as 8, this as 9. So, that is my total moment capacity of the elastoplastic section, which is sigma y B H square by 4, 1 minus E square by 3 H square. Okay. We also know that MP is sigma y into ZP for rectangular section ZP is B H square by 4. We already said that. Okay. So, we can now write, we can rewrite the equation 9 as M equals, this part I am replacing as MP 1 minus E squared by 3 H square. Okay. That is equation number 10. Okay. Where E is the depth of elastic core in the section. So, for the section, for a plastic section, E will be 0. For a complete elastic section, E will be equal to what? Depth of the cross section, is it not? Okay. So, one can easily find out this. So, we will also try to expand this. Let us say MP is sigma y and ZP, M elastic is sigma y Z elastic. So, let us say MP by ME is sigma y ZP by sigma y ZE, which gives me that shape factor. So, shape factor, which is a geometric property, is also the factor of additional moment capacity of the plastic section beyond elastic section, correct, because MP is shape factor of ME. So, shape factor is an additional capacity indicator of the fully plastic section from the fully elastic section. Please understand friends, at this stage stress is not exceeding yield, but still the term plastic is used because the deformation is plastic, not the stress. Okay? That is what it is. Having said this, let us try to work out shape factor for a rectangular section. It is a geometric parameter. Let us do it for a rectangular section. Let us take this H. Okay. So, this is top area, bottom area. We call this as A1, this as A2, and this as H by 2. This is also H by 2, is it not? So, we know A1 is equal to A2 is B H by 2. We also know y bar 1 is y bar 2, which is H by 2, sorry, H by 4. This is H by 4 friends. So, ZP is actually, the equation is A by 2 of y bar 1 plus y bar 2, is it not? That is the ZP value. We had somewhere here this. So, this ZP, is it not? This is ZP. So, that is what we are trying to say here. Y bar 1 plus y bar 2, correct. Let us substitute that here, which is going to be A by 2 of H by 4 of twice, which becomes B H square by 4, and ZE elastic is B H cube by 12 by H by 2, which becomes B H square by 6. So, shape factor as we know is ZP by ZE, which is B H square by 4 B H square, which becomes 1.5. So, shape factor for rectangle is 1.5. So, the plastic capacity of rectangular section is 50% more than elastic capacity of the same section. So, friends, in this lecture we discussed the importance of shape factor, the important philosophy of plastic design. We also learned how to find out the depth of elastic core, and we understood how to arrive at the shape factor for different geometry, isn't it? I hope you will follow these lectures and revise them regularly, and you will apply for more examples. Look into my advised textbooks, recommended textbooks for this course, acquire a copy, learn them. There are many MATLAB programs available in this, which will help you to solve many problems as exercises and for intensive learning. Thank you very much. Have a good day.